Welcome back, everybody. So last time we talked about a really powerful technique that can be used in order to be able to implement sums of unitaries on quantum computers. The catch is, of course, it came with a particular success probability assigned to it. And these success probabilities, as we'll see in this discussion, can actually get kind of bad in some contexts. So I'm going to talk about that now, talk about how we can use amplitude amplification to try to mitigate that, and discuss a very particular case where we can use a flavor of amplitude amplification known as Oblivious Amplitude Amplification to basically be able to do recursively linear combination of unitaries over and over and over again until you've done a large algorithm. So that's what we're going to be talking about today. So let me share my screen and jump over. So the basic idea, again, with linear combination of unitaries, as you recall, is that let's imagine what we want to do is we want to build a matrix A, which is the sum over J of alpha J uj, where alpha uj, these are all unitary, and the alpha j's we're assuming are positive, so greater than or equal to 0. And the basic idea is that this method ends up giving us a way to build a larger unitary, let's call this unitary L, such that in upper left block of this block matrix, we could we encode A over alpha, where here alpha is defined to be the sum over J of alpha sub J. Okay, so in this sense, this is known as a block encoding because what we're doing is we're encoding this matrix A, which could be any matrix we feel like, inside a block of a larger unitary matrix. Okay, so this is basically the entire idea of block encoding, and linear combinations of unitaries gives you one way of providing a block encoding for a particular matrix. And the circuit that we used to do this was of the form prepare, select, prepare, dagger. And this was assumed to be 0 at the top. This is psi. And we want to assume that we get success if this is equal to 0 tensor M. Back up. So the idea basically from the way that this block encoding ends up working is that we want to apply this block matrix on a state of the form 0 tensor M psi. Actually, this is 0 down here. And then in the event that when we multiply this, we can end up seeing that the 0, the block vector that we end up getting out of this will be 0 tensor M A psi over alpha. Well, actually, this isn't necessarily 0. This is question mark. We haven't worked that out. And furthermore, it's actually easy to see that the probability of success of getting this is this amplitude squared, which is just psi A dagger A psi over alpha squared. Okay, so this is one of the reasons why when we're using these techniques, alpha is so vitally important, because as alpha grows and grows and grows, the probability of success can shrink to next to nothing. But that isn't the only problem. So let's go through another example. Let's say what I wanted to do is I wanted to apply A squared to a vector. So we would like to take a vector psi goes to A squared. Well, there's a couple of ways that we could apply it. Yes, we could use the fact that if A is the sum over J, alpha J, U sub J, then this implies that A sub J squared is also a sum of unitaries. We can write this, or A squared is the sum over JK, alpha J, alpha K, U, J, U, K. Okay. So that we can also represent it as a linear combination of unitaries. But to motivate this problem, let me actually just talk about how we could implement this directly. So if we implement this directly, then what we end up getting is we would get a situation like this. We begin with 0 tensor M up here. We then would apply, our prep, then select, and then prep dagger at the top. And we've got a state psi coming through at the bottom. And then we would feed this into the, we would then measure these. And in the event that we end up getting all zeros, we would then go through and do the exact same thing. And just to remind you, the definition of prep acting on 0, prep is the circuit that prepares the coefficients for the sum of unitaries. It produces square root alpha sub j over alpha j, and select acting on j and psi ends up providing us the individual unitaries that we have in the decomposition. So this will give us uj psi. All right. Now, this is the particular, so this is the decomposition for it. Now, we discussed that the probability of success for doing this once is equal to, well, psi a dagger a psi divided by alpha squared, okay? And so this over here, we could actually lower bound by saying that this is less than or equal to the minimum eigenvalue of a dagger A divided by alpha squared. And so therefore, this whole process has to succeed once here, and then again at the end. So the probability of applying a squared from this is therefore greater than or equal to lambda min of a dagger A divided by alpha squared, all squared. And furthermore, if we generalize this exact same idea and want to apply it k times, then this probability of success is going to drop exponentially. So this might be okay for many contexts. In fact, it often is, if we want to just apply an arbitrary matrix once. But if we want to apply that matrix a bunch of times to a particular state, then we end up getting this worst case success probability fall off that's exponential. Now, note, even in the case where this bound is tight, like for example, if A is unitary, then the probability of success is just 1 over alpha squared. We'd see that there actually the probability of success still falls off exponentially. So that's a problem, but I mean, could we use amplitude amplification to be able to get around this problem? So that way it succeeds with 100% probability. Well, amplitude amplification is not a perfect panacea for this. So if you recall, the way that amplitude amplification worked is we needed 2 spaces. We needed a good space and we needed a bad space, okay? So in our case, let's just take a look at this. We want to boost the probability of success, right? So we want to boost the probability that when we measure these m qubits at the top that we get all 0. So the good space then can be defined by a projector onto all states that are defined to be good, which is of the form PG is equal to 0, 0, tensor M, tensor identity acting on the input state. So we're now calling all states that are of the form 0 tensor M good, and all states that aren't of that form bad. which of course the projector under the bad space will be 1 minus the projector under the good space, because we're assuming that all states are either good or bad. Okay, so that is how amplitude amplification works. Now, the idea then is we would take our entire quantum circuit, or we'd begin with a state actually 0 psi. Then what we would do is we would then map this to L 0 psi. And I'm going to define this to be a state that I'll call psi init, just to make sure that it's disambiguated from the input state psi that we put in. Okay, so this circuit again, L is just the thing that looked like this, right? It's the prepare, select, prepare circuit. Okay, so this is our initial state psi. So if we applied amplitude amplification and we want to boost the probability that this register is a 0 tensor M, what we need to do is we can end up viewing this as in a two-dimensional space spanned by the initial state, or psi init, where I don't mean the initial psi, I really mean this guy here, like the thing whose probability we want to boost, and its orthogonal complement over here inside this space. And so the basic way that we ended up building this is we built a walk operator that was of the form negative identity minus 2 times the projector onto good times times the projector onto init, which actually, you know what, let me just write that projector out. I think that'll be a little bit clearer. That projector onto psi init is just of the form psi init, oops, and then multiplied through by the reflection about the good subspace, which is of that form. Okay, fantastic. So this is our walk operator. Now, if we applied this walk operator, WP, to the state L0 psi, then recall that our probability of success that we ended up getting after P iterations is going to be sine squared 2P plus 1 theta, where theta here is defined to be the arcsine of the square root of the probability of success at 0, which of course in our context is the arcsine of the square root of the expectation value of psi a dagger a psi divided by alpha. Okay, cool. So then in that case, our probability of success is that. And the value of P that we're going to need in order to be able to boost this success probability to 1 will be P in order alpha divided by the square root of psi a dagger a psi. All right, wonderful. So this is how we can use amplitude amplification to boost it. And every step along the way, we can make this deterministic because we know the success probability. It's just this guy. So if we know what the success probability is, then we can boost it to 100%. And well, I guess actually I should say we may not necessarily know this guy, but certainly in the case where A is unitary, then the numerator is 1, in which case we can compute alpha because alpha is just the sum of the expansion coefficients that were provided as input to the problem. So in that case, we could figure it out. But I guess I spoke too soon. The broader case where we don't know what the input state psi is, the numerator here might be very difficult to carry out. So it could be hard to make this deterministic. But for the sake of argument, let's just make it deterministic, because even then things are going to go wrong in a hurry. So the number of operations we need, it scales linearly. But now let's, wow, okay, this is happening again for some reason. Interesting. Wow. PowerPoint, how you have betrayed me yet again. Okay, well, time to make a new presentation. I swear, Microsoft absolutely hates me. All right, so now we have these particular, okay, so let me actually just go back to the other deck and hopefully copy and paste the relevant stuff over if there was anything relevant. Ugh. Okay, sure. Cool. So this ended up giving us our probability of success. So the number of operations that we ended up needing was, of course, scaling like the reciprocal of this guy over here. Okay. So another way of writing this is, I guess, the number of operations that we need would be in order alpha divided by the square root of the minimum eigenvalue of A dagger A. That certainly is true. Okay, wonderful. So that's cool. But now, if we're chaining this together, let's think about what we would need to do in order to be able to amplitude amplify for the next step. Well, our next step begins with a state that's of the form A psi divided by the length of A psi. Okay, if we've succeeded, we've applied A. So our resulting quantum state, after properly normalizing it to become a unit vector, is that. Okay, great. So now what we're going to want to do is we're going to want to apply L to this state to 0. Sorry, I forgot to include the extra m qubits at the top here that are needed. Okay, we apply L to this, and then I'm going to call this state psi init prime. So we can do the exact same thing in principle. We can begin with psi init prime, and then carry out our sequences of reflections. We can reflect about first this axis, and then we can reflect about psi init in order to do a rotation up. And again, if that's theta, this is 2 theta, and we can just rock on to the solution. But the real question is, how do we carry about this reflection? Well, we need to reflect about psi init prime, and that reflection is of the form identity minus 2, 0, L 0 tensor M A psi 0 tensor M A psi A dagger. Okay. Now this reflection operator might look like I screwed up the orderings for when I was taking the adjoint. Recall that the adjoint has a distributive property over tensor products. A tensor B adjoint is equal to A adjoint tensor B adjoint. However, over ordinary products, it has the opposite property. It's B dagger, A dagger. Now, because of the fact that Dirac notation has an implicit tensor product structure, psi phi is defined to be equal to psi tensor phi, then the adjoint rule for quantum states under this notation looks a little bit different than you would have for ordinary matrix multiplication. So this is one of the downsides of Dirac notation, is that it can get kind of a little bit confusing about how to apply adjoints to the implicit tensor products that you have when you express it. But it's not so bad, just you have to remember to flip it. But it can get, if first time you see it, it can get kind of confusing, and it makes it look like I made a mistake when I was computing the adjoints here. But I think in this case is perfectly fine, with the exception that I think I need a L dagger here. All right, so this is the reflection operator. And the key bit about that reflection operator is it has this value A associated with it. So in order for us to carry out this reflection operator, we would need to apply A. But to apply A, we actually needed to carry out this and a reflection operator based on that. So this is creating like a house of cards situation here. We can do this in order to amplify the next step, but in order to do that, we need the previous step, which we already amplified. Going through the cost of this ends up leading to the conclusion that if you want to carry this out, you can do it, but it's going to take exponential time. And so that is just not on the table, because obviously we're not saving anything if we do that. So can we deal with this problem in a smarter way? And the answer is, in some cases, yeah, actually we can. We can use a different flavor of amplitude amplification that doesn't require a full reflection about the initial state. However, we need that A dagger equals A inverse, i.e. unitary. And this form of amplitude amplification is what we call oblivious amplitude amplification. Okay, so let me show you how it works. Well, oblivious amplitude amplification consists of two reflections, just as it did previously. The two reflections are of the form identity minus 2pg over here, just like before. We'll put a minus sign here for aesthetic reasons. And then the next part is identity minus 2 L acting on 0, 0, tensor M, tensor identity L dagger. Where again, L here, this is the LCU circuit that we did previously, okay? So we can see that this actually ends up taking the exact same form that we ended up having previously, with one notable exception, right? Before we had a reflection about our initial state. So if we took a look at that version, what we had here is we would have specified this projector to be a projector on the side. But instead, we've replaced that with an identity. What the identity is telling us is that we actually don't care what the initial state is for this version. And it's going to turn out that under the assumptions, and only under the assumptions, that A dagger is equal to A inverse, that actually it's possible for us to underspecify this second part of the reflection and only reflect about the 0 register, or in some sense, the 0 register after doing the basis transformation into the circuit. So that is the form of the whole thing. So now let's go through and analyze this. The way we're going to analyze this is I'm going to define this operator to be W. And we'll go through the analysis just like we did for the amplitude amplification. This process is a pair of reflections. And if you invoke Jordan's lemma, you can see that a pair of reflections will always end up leading to a rotation. However, ultimately, you don't need to know about Jordan's lemma, but Jordan's lemma just ends up inspiring the fact that these two reflections are going to basically be carrying out a reflection, as before, about the initial state, or subspace that contains the initial state. And then we're reflecting about, well, technically the space orthogonal to the good space which is this line, and that's why the negative sign is included, to make it kind of aesthetically nice when we draw this picture, even though it kind of doesn't matter because it's a global phase, then this angle is 2 theta. And so the exact same analysis is going to end up holding. And so we'll carry through the algebraic derivation that we did before. So the walk operator here, we can end up expressing inside this 2-dimensional subspace, and I'll denote this by the state we called psi init over here, and a state I'll call W perpendicular, okay? Where W perpendicular is defined to be the orthogonal complement of W acting on psi init from the state psi init. Didn't give myself enough space. Let me rewrite this. Identity minus psi init W acting on psi init divided through by its length. So that way the W perpendicular quantum state is a properly normalized quantum state. So we just divide through by whatever length is needed to turn this into a unit vector. Okay, but we're not actually going to really care about this. The thing that we at least at first, the thing that we ultimately end up caring about is the form of the matrix confined inside this 2-dimensional subspace that I've drawn here, where this vector over here is psi init, and then geometrically, this vector over here is W perpendicular. Okay, so then inside this subspace, we have that the matrix action is W init, psi init, psi init, W perp, and we have then W perp, W psi init, and then last but not least, we have W perp, W perp. All right, so this is the operation inside the 2-dimensional subspace. Now, in the interest of time and your patience, I'm just going to compute this matrix element. The rest, you can end up seeing how you would find it from that. So that matrix element, psi init acting on W, psi init, this is, of course, equal to negative psi init identity minus twice the projector onto good, which is 0 in our case, tensor the identity on the psi state, and then we're going to multiply that by identity minus twice L 0, 0, tensor M, tensor identity, L dagger, psi init. Okay, fantastic. So now let's actually just express psi init. If you recall, psi init was defined to be L times 0 psi. So therefore, this whole thing we can end up writing as 0 psi. Yeah, 0 psi, L dagger, identity minus 2, projector onto 0, tensor M, tensor the identity onto the psi state because we're only considering the zeros as flagging whether or not a subspace is good. And then we multiply this by identity minus 2L, 0 tensor M, tensor identity. Now the L dagger cancels the L in the definition of psi init. So we're just left with 0 psi. All right, wonderful. So now, oh, I'm sorry, that's actually not quite right here. The L dagger will cancel it there, but not on the other one. So what is right is this. We can factor the L out in front. The reason why is the identity multiplied by L is going to give us a factor of L, and the L dagger multiplied by L, that's going to die, but we still have this extra factor of L in front. So by factoring out the L, we can end up seeing that we have this expression. Now, actually, the state, and I dropped a minus sign here. Now, the state over here has 0 in the first qubit. Therefore, this reflection operator acting here will flip the sign of this quantum state. And so this will give us 0 psi L dagger identity minus twice the projection onto 0 tensor identity L 0 psi, where the minus sign from the reflection operator has killed this minus sign out in front. All right, great. So now we're at a much simpler place. But if you recall, our matrix L that we ended up forming, we showed using the LCU theorem that this is of the form A divided by alpha and a bunch of question marks out here. And so if we pick this block, this implies that A over alpha is just the subblock of the larger matrix. And we showed that we can write that as in the following way. 0 tensor identity L times 0 tensor identity. Okay, so that just picks out this particular block in the output. Okay, and that's really going to help us. The main reason why that's ultimately going to help us will actually be apparent in a moment. Okay, first, let's distribute this multiplication through. The L and L dagger cancel. These two have an inner product of 1. So this is actually just going to be 1 minus 2, 0 psi L dagger 0 0 tensor identity L 0 psi. Okay, which we can refactor as 1 minus 2 psi 0 tensor identity L dagger 0 tensor identity times the exact same factorization on the right-hand side, which is 0 tensor identity, but now we don't have an L dagger, we've got an L. So we need to put an L there. And 0 tensor identity, all sandwiched between psi. Okay, now this, we recall, is A over alpha. So from that, we end up with the following expression. Okay, we've got this, and now we're going to simplify it by taking this to be equal to 1 minus twice A dagger over alpha psi A over alpha from the second one, from this guy over here, psi. This is equal to 1 minus 2 psi A dagger A psi over alpha squared. So that is our expression that we end up getting in the end for the resulting state. Now, we assumed that A dagger equals A inverse. Therefore, under those circumstances, this is just 1 minus 2 divided by alpha squared. Now, if we define our success probability, P suck, if we applied 0 iterations of this, this is just 1 over alpha squared, right? As we can see from this analysis directly. Well, our probability of success is 1 over alpha squared. So this ends up setting our angle corresponding to this, where we have sine squared theta is equal to 1 over alpha squared, implies that theta, the analog of theta for our amplitude amplification, is just the arc sine of 1 over alpha. Wonderful. And so that ends up implying that if we write it in this particular way, this ends up giving us 1 minus 2 sine squared theta, which of course is equal to cosine 2 theta, which corresponds exactly to our intuition from the geometric picture. We expected that these two reflections should rotate up our initial state by an angle of 2 theta in this subspace. And it does if this numerator is 1. And a sufficient condition for this numerator being 1 is if if A is a unitary matrix. So if A is a unitary matrix, then this process actually goes through just like ordinary amplitude amplification. When we work out the rest of the elements using the exact same algebraic techniques that I mentioned, the rest of the elements that we end up getting will be cosine 2 theta, sine 2 theta, minus sine 2 theta, cosine 2 theta. Okay, and what this ends up meaning is that if we have that the probability of success is known beforehand, and that's equal to 1 over alpha squared, then applying WP to a state L0 psi, this will actually end up giving us a state that will be the state that we want. It will be equal to 0 a psi sine squared of 2p plus 1 theta plus some cosine squared of 2p plus 1, some there shouldn't be a ket here, of some orthogonal state psi perpendicular. Then the probability of us successfully applying A to psi over here is given by this. And so if theta is of course equal to the arc sine of 1 over alpha in our case. And this implies that the number of applications of W the number of times that W needs to be applied to get P suck equals 1, using again the trick that I mentioned last time where we lower the success probability purposefully for the circuit, is in order. It's just in order alpha. Okay, so therefore we can do this in time order alpha. So if we want to apply A to the K on psi, well, what we can do is now, because we don't need to reflect about the initial state, we can carry this process out K times. And so the cost, because we didn't need to do this chaining that I discussed previously, where we need to reflect about the initial state, we only need to reflect about the two spaces that the initial state is in and also the good state that we want. Then we can apply this unitary matrix to the kth power in time order K alpha. And this is not exponential anymore. So this is really important because it shows that what we can do is if we want to build a matrix that's unitary using a linear combination of unitaries, we can totally do it. And we can chain these things together at cost that scales linearly with a number of operations, which is the best that we could possibly end up hoping for in generality, because sublinear would allow some really, really crazy consequences. So that is how Oblivious Amplitude Amplification works. And it's the cornerstone of ideas that are needed in order to be able to translate this over to a quantum simulation method. So hopefully that made some sense. Now, this derivation is a little technical. The high level thing that you minimally need to understand for this is that if you're using linear combinations of unitaries, then you can apply any matrix you want. It's just you can't necessarily chain them together in some kind of efficient way. Oblivious amplitude amplification allows you to get around the drawbacks of amplitude amplification by not requiring you to reflect about the initial state if A is unitary. And this gets around that chaining problem and allows us to efficiently apply LCU as a circuit primitive that we can use to do a bunch of different things. And we'll see some of these things later. So, okay, well, hope you all enjoyed it, and see you all later.